Hi everyone, Mrs. Hanson here. Continuing our work in Chapter 7, we have been investigating bimolecular collisions in a nucleophilic substitution, and today I'd like to continue our work investigating bimolecular collisions, but with the result of an elimination. And we know that SN2 and E2 are actually competing reactions. So let's kind of just set our stage. Elimination 2. The 2, of course, we know means bimolecular collision, and E is going to stand for elimination. Since this is an elimination, we have a little bit of a vocabulary word change, where instead of having a nucleophile, as we did in a substitution, we now involve a base. And let's make sure we understand those definitions. When I had a hydrocarbon, let's just suppose I draw a hydrocarbon, and I put on a halogen, the halogen becomes the leaving group. And we know just based on the polarity of this bond that this carbon then becomes an electrophilic center, and the chlorine, of course, is electron rich. So when we have a nucleophile, such as hydroxide, the hydroxide acting as a nucleophile then says it's being drawn towards the electrophilic carbon, and that then makes the leaving group leave. A nucleophile seeks an electrophile. And when that happens, we have a substitution occur, and we've learned that we would have an inversion of the configuration. We call that a backdoor attack. And so instead of having a wedge on the priority of chlorine, we end up having a dash, and we've turned our alkyl halide into an alcohol. That is a substitution reaction, turning one functional group into another. And an inversion with this bimolecular collision. And we remember learning that polar aprotic solvents work best in promoting nucleophilic substitution. But now all of a sudden, if I redraw this particular substance, and I just think of this in terms of acid-base chemistry, we could have the same hydroxide with its electron-rich area acting as a base. Instead of a nucleophile that seeks an electrophile, it now seeks a proton. And let's keep in mind that we labeled this the alpha carbon. The carbon that's attached to the leaving group is known as the alpha carbon. But more interesting now is the beta carbons. Those beta carbons are one position away from the alpha. So we have hydrogens in the beta position here. There's 3 of them at the terminal end, and we have 2 hydrogens that are in the beta position at carbon 3. So if hydroxide is acting as a base, it seeks a proton. That's what acid-base chemistry means, is that a proton is transferred. And the protons that it seeks are on the beta position. And since we see that there are actually 2 choices, we undergo what's called a 1-2 elimination, or sometimes you'll just hear it called beta elimination, where the proton is removed from that beta carbon and the halide acts as the leaving group. One possible outcome is to take this hydroxide and pluck a proton from the first carbon in that alkyl halide. And when it does so, that proton, you know that the proton would go and form the conjugate acid of hydroxide, which would be water. This bond then collapses and the leaving group leaves. The leaving group picks up those electrons in that bond and just takes it with them. So of course we would have a chloride as a resulting end product as well. But when I take off this proton, the base removes a proton has been transferred, acid-base chemistry. What we see there is that a bond collapses. So one possible product here was forming 1-butene, an alkene that removed a hydrogen from carbon 1 in that 4-carbon chain. A second possible position was looking at these hydrogens in the beta position. What if instead of going to carbon 1, we went to carbon 3 and removed that proton? So just thinking about that chemistry, if an OH group were to come in and take this beta proton, it would then force the bond to collapse between carbon 2 and 3, and the leaving group then leaves. So a second position could have been 2-butene as our resulting alkene. This is something we will study in depth. We see that we have a mixture, a least substituted alkene in the terms of 1-butene. The least substituted means that it has the carbons that are in the double bond, versus over here, this is the more substituted product. And we'll learn that these are called the Hoffman, which is least substituted, and the Zaitsev, which is the most substituted alkene. And this is where our journey is heading, comparing SN2, bimolecular substitution, into a new process, a new mechanism known as E2, bimolecular elimination, where we see we have a mixture form here of 1-butene or 2-butene, and this could actually, kind of thinking about mechanism. The stress here I want to make sure we see is that when substitutions occur, we have a nucleophile, because a nucleophile seeks an electrophilic carbon. When we have elimination, we call these same molecules, perhaps even, but they're now called bases, because a base takes a beta proton, forms its conjugate acid. Leaving group still leaves, but the result is a pi bond. So the E2 mechanisms favor, making these strong bases of a conjugate acid. We think about E2 elimination as forming a pi bond or a double bond, where that's not the case of substitution. Substitution converted one functional group into another. Elimination turns an alkane into an alkene. Let's keep investigating. When an alkyl halide is treated with a strong base, it undergoes beta elimination. Make sure we're using these vocabs correctly. A base is looking for a proton. A nucleophile is looking for an electrophile. When a substance acts as a base, a proton is transferred. And so here's our X. This is our leaving group, typically a halogen here. And I have a base. I know that the alpha carbon is the carbon that's attached to the leaving group. I look around and find all beta carbons and look for their protons. A base is going to transfer a proton from a beta carbon. And when it does so, the leaving group leaves, it takes those electrons there, and the pi bond forms from the collapse of the hydrogen. And so we form a conjugate acid of the original base, and of course the halogen acted as the leaving group. And now we have a new alkene in terms of our desired product. The base reaches out for the beta proton, that bond collapses, the leaving group leaves. This is a concerted mechanism. That means this all happens in one step. There is a transition state where bonds are breaking and new bonds are forming, but it is a one-step mechanism, bimolecular. So notice the base abstracts the proton, that bond collapses, forcing the leaving group to leave. Now think about that just in terms of stability of the carbon. If you redraw this and just think about carbon always requiring 4 bonds, if I only abstract the proton, right, it's gone, and this bond then collapses, there would become a double bond, but this carbon would be too unstable because it has 5 bonds. That's not allowed. That's a cardinal rule you cannot break. That's the driving force behind the leaving group getting shoved out, so that carbon still only retains 4 bonds, so minus the leaving group, and you're left with 4 bonds that way. So when that bond collapses, forming an alkene, the leaving group must leave to create 4 bonds on the carbon, the most stable configuration. And again, a very concerted mechanism, an E2 bimolecular collision. Let's remember, we still have a next lesson for SN1 and E1, which is our stepwise mechanisms. SN1 would be nucleophilic substitution, unimolecular, and E1 is elimination unimolecular. And we're remembering that the very first step is the leaving group leaving, that will be the rate determining step. The leaving group leaves. And what will be unique when we get to this step, we have a carbocation intermediate. And that carbocation, of course, we know will have an sp2 hybridized electron deficient carbon. That will be the very first step in an E1 as well as an SN1 mechanism. So the leaving group must leave before anything else can happen. Of course, we know in an SN1, the substitution, we know that we would have a nucleophile seeking the electrophile. In an E elimination, we have a base, and the base transfers a proton, forming an alkene. I bring this up so we remember this is a next lesson coming. We've studied SN2. We are now investigating E2, but coming are the mechanisms that are unimolecular, E1, SN1. All right, so our focus now, comparing bimolecular collisions that are substitutions and bimolecular collisions that lead to eliminations. This elimination is a concerted, meaning one-step process. The base removes the proton from the beta position. Just remember what that means. When we look at a beta position of the leaving group, and the leaving group could be a halogen, the beta position is one next door to the alpha position. So this is where our focus is. Are there available protons on the beta carbon? So just as if we had an SN2 mechanism, we see a lot of the same similarities for E2 mechanisms in terms of kinetics as well. If the rate is equal to the rate constant K, and here we would say times the base raised to the first power, times the alkyl halide that we've been calling the substrate, the alkyl halide raised to the first power. This kinetics would say it's first power, first order with respect to the base, first order with respect to the substrate, and it would be a second order overall. So a direct correlation to the speed of the reaction, the kinetics, to each of those individual molecules. Thinking about thermodynamics, you'd have the reactants in a one-step product leading to the products. So the reactants turn to products, and at the top of the energy barrier, you would have a transition state, that's that double dagger sign, where you would see the bonds forming from the base, the leaving group leaving, I'll write Lg for leaving group, and then whatever else is attached to that carbon. But bonds breaking and new bonds forming at the top of the energy barrier. So the kinetics looks very similar to the overall SN2 mechanism. So the transition state for that SN2 reaction would place the nucleophile on that carbon. Here, of course, the transition state for this elimination reaction focuses here, and I'll just put those guys next to it, but on the beta carbon as well. So we have to kind of consider this guy and the abstraction of that proton. So we'll investigate this, but just saying very similar, where we have transition states at the top. There are no intermediates since it's a concerted mechanism. First order with respect to the base, as well as the alkyl halide, second order overall. And we answered a question very similar to this for SN2 mechanisms. Here's the next homework question that has you consider the same thing for an E2. So notice what we have on the arrow. We see a base. Sodium is a spectator, so the base, of course, is simply hydroxide. I have a beta position here and a beta position here. Each one of those has two hydrogens. So I have 4 equivalent hydrogens that I can eliminate. Thinking about the mechanism, just to emphasize, what happens is the base reaches out for a beta hydrogen. The proton is abstracted. That forces this bond to collapse, which forces the leaving group to leave. We'll form the conjugate acid of that base, plus the leaving group with its extra set of electrons now, chloride, and we formed an alkene, and since this would be the same, this is equivalent, if you had gone to the other proton, the one at the top of the house there, if I formed my double bond here or my double bond here, those are indeed equivalent. We have cyclopentene either way. But what about the kinetics? What happens to the overall rate if the concentration of chlorocyclopentane is tripled? Well, remember, rate is equal to K times the concentration of the base to the first order times the concentration of the substrate to the first order, which means second order overall. If you doubled the substrate, you would actually double the rate. 2 raised to the first power is 2. So letter A, the rate, we tripled it. If we tripled it, 3 raised, that's what we did, we tripled it. And so whatever you do to the substrate, the rate will follow along. So if you triple the substrate concentration, the rate will also triple. Letter B. If the cyclopentane remains the same, but you double the sodium hydroxide, again here you would simply double the rate. Rate is equal to the base to the first order, so if you doubled the base, you will double the rate. The other one gave us a triple the substrate, it's first order overall, so you can see you would triple the rate. And in letter C, what if the cyclopentane is doubled? And what if the base is tripled? 2 times 3, it would be going 6 times faster. First order with respect to each of the reactants. Thinking about the bimolecular collision on the effect of the substrate, we have to consider steric hindrance and how this mechanism can be achieved. Consider a reagent such as sodium hydroxide, a very strong nucleophile, as well as a strong base. The hydroxide, OH negative, can be a nucleophile if it's seeking an electrophilic carbon. Then the word for it is a nucleophile. Hydroxide can function as a base if it's going for the beta hydrogen so that we have a proton transfer. Notice this substrate, the alkyl halide, and kind of look and see what's happening. You have a big bulky group here. These are all methyls that are coming out. See how we're kind of drawing all these methyl groups. And notice that this is the leaving group, and it's some halogen, the leaving group. In order for the hydroxide to be able to act as a nucleophile, this is the carbon that it's seeking. This is the electrophilic carbon based on the polarity. This is the partial positive. The leaving group is very electron rich. How well can this target be hit in a bimolecular collision by a base such as hydroxide if there's all kinds of steric hindrance covering that electrophilic carbon? Tertiary substrates are often too sterically hindered, and the nucleophile cannot penetrate and attack the electrophilic carbon. So this is sterically hindered, and therefore I can't get to this target. Even though I have a nice small base here, or a nice small nucleophile, it still is being prevented from getting into a successful collision of that tertiary carbon there. But notice here the beta hydrogen is very easily abstracted because it doesn't have to make it all the way to the center where the electrophilic carbon is. You're looking at the beta position carbon, and the hydrogen here is a nice target. So tertiary substrates favor elimination. And we'll investigate some of that more towards the end of the chapter as we decide, looking at our base, looking at our substrate, we ultimately need to make the decision, are we going to favor E1, E2, SN1, or SN2? And these are just some of the considerations. Do we have a sterically hindered alkyl halide, which we call the substrate? If so, we can see just based on steric hindrance that you're more likely to see an elimination where the beta hydrogen is a much easier target than a substitution where that carbon, the electrophilic carbon, is very hidden behind its steric bulk. All right, so we can see that elimination reactions form alkenes. And so next section, we're provided an opportunity to review some nomenclature, alkene nomenclature. So since the product of an elimination, I don't care if it's E1 or E2, produces alkenes, let's review the nomenclature of properly naming double bonded compounds. Alkenes are given IUPAC names using the same procedure to name alkanes, but with a few minor modifications. First, we need to identify the parent chain that must include the carbon-to-carbon double bond. Then we will identify and name any of the substituents, giving it a number and a prefix if necessary to indicate quantity. This is a very important part. The carbon-to-carbon double bond receives the lowest possible number. Even if we run into another substituent group first, we want to make sure we're numbering from left to right or right to left to make sure that the double bond gets the lowest number. Then all the other numbers are placed. And just within alkane nomenclature, we number the substituents before the parent name and alphabetize those substituent branches. And the ane for an alkane, which were all single bonds, here the endings become enes for alkenes, which will have the double bonds. Let's try some. Step number 1, we said we need to identify the longest parent chain that must contain the double bond. So for instance, here I can see that I have a 5-carbon parent chain. If they are all single bonds, all sp3 hybridized, we would end this with ANE. This is a saturated hydrocarbon. Now all of a sudden I'm noticing that between carbon 1 and carbon 2 is a double bond. So now all of a sudden, since we're unsaturated, there's a presence of a double bond, that the ending will change to ene. I'll let you know that between carbon 1 and carbon 2 is a double bond by placing a locant, a number telling you where, and changing the ending from ane to ene. In this example, this is a saturated hydrocarbon, an alkane. So I would number this, making sure that I just check both directions so that the branch would receive the lowest number possible. This is an 8-carbon chain. I'm going to number right to left so that I can get the substituent branch, the lowest possible number. On carbon number 4 is an ethyl group of an 8-carbon chain. So this would be 4-ethyl octane. Now let's look at the alkene. I notice now that I had created a double bond between carbon 1 and 2, and I must make that my parent chain. The parent chain has to contain the double bond, even though if I number in this direction, I can find a longer carbon chain. 8 is certainly longer than 7, but the green numbering system did not include the double bond, so it is not correct. I would now tell you at carbon number 3 is a propyl group in a 7 carbon chain where the double bond is located between carbon 1 and 2. So now you'll hear this as 3 propyl, 1 heptene. When you identify and name the substituents, make sure that you arrange those numbers to give the lowest number possible to the double bond. Even if I can get to the branch from other direction, you want to make sure that you're numbering the double bond with the lowest number possible. And so thinking about how I would number this compound, I could see at carbon 5, 5, and 6, there are 3 methyl groups. And between carbon 2 and 3 of this 7 carbon chain, there is a double bond. Notice that 5, 5, 6 gives us the substituents, but that's, and just to compare, at carbon 2, 3, 3, you would have methyl groups. If the double bond were located between carbon 5 and 6, you would name that 2,3,3 trimethyl 5-heptene. But we're emphasizing the priority. The priority is coming from the double bond location first. And so clearly we see that 2 is a lower number than a 5, so this wins. Not based on the substituent branches, but lowest number to the double bond, and then let all the other numbers fall into place. We also know that there's some stereochemistry to consider, and we practice that in our chapter 5 stereo conformations as well. Since we're producing double bonds, these alkenes, we have to think about stereochemistry as well. And we have to make sure that all conformations have their own unique name. And so we have to add the E or the Z, or you could consider cis or trans, if appropriate, when naming the alkenes. Remember that E represents opposite sides of priorities of the pi bond, and Z represents the same side, the same side of the pi bond for priorities. And so a moment ago when we named 5,5,6 trimethyl 2-heptene on the previous slide, we were not quite done yet. I had to find the configuration for the stereochemistry to give it its own unique name. So find the 2 carbons that are in the double bond and assign priorities. The priorities are given to the higher atomic number. So here priority is given to the carbon group, and remember, even though it's not shown, that's a hydrogen for the 4th bond. Carbon is a higher priority than hydrogen. And even though it's not drawn, I can see this is hydrogen on carbon 3, and so the priority would be given to the carbon up here. So the pi bond creates this plane, and these are on the opposite sides, so this is the E configuration. So altogether, E, 5,5,6 trimethyl hept-2-ene, or I'm more likely to say trimethyl 2-heptene. But it is, it's not often, but it certainly is IUPAC accepted to place the number right before the ene, but you're more often going to see it in front of the parent name. So that EZ configuration comes out again. It did in chapter 5, and it does so here as well. You find the priorities. The priority is the higher atomic number in each carbon. So when I'm comparing carbon to fluorine, fluorine is of higher priority. When I compare hydrogen to nitrogen, nitrogen is of higher priority. And since we have higher priority on the same side of the pi bond, think of that as the Z configuration. Here is the planar area of the pi bond, and now they're on opposite sides. That's the E configuration. A nice review there from Stereochemistry. So let's practice. You're going to have quite a few of these just to practice naming. Provide an IUPAC name for each of the following. So I'm going to just start by numbering the chain and decide which direction would give me the lowest number on the double bond. Let's just number them both. Didn't work out well. 1, 2, 3, 4, 5, 6. So the double bond is at number 3 when I arrive from counting left to right and when I arrive counting right to left. So which way wins? Well, we get double bond at carbon 3 both directions. So now what we need to consider is which direction would give the methyl branch the lowest number. So consider the branching next. And that should have the lowest number prioritized. And so this 3, of course, is smaller than the 4, so we need to number left to right to be sure that the double bond is also given the priority, but if it's a tie, go to the substituent which gets the lowest number. So far, we have a methyl at carbon 3. Our double bond is also at carbon 3, and it is a 6-membered chain. So we have 3-methyl 3-hexene. But let's also consider the stereochemistry as part of our name. So let's find those carbons in the double bond, right? Those are the 2 carbons, and I want to see what they're attached to. So I'm looking at what each carbon is attached to and deciding which one is of higher priority. So in this carbon, I see it attached to 1 carbon, and up here I see it attached to 2 carbons. So this is of higher priority. And in this carbon, on the right side of the double bond, I have a hydrogen versus a carbon, and so therefore the carbon is of higher priority. These are on the opposite sides, so this will be the E configuration. E, 3-methyl 3-hexene. How'd you do? Okay, let's try another. There's plenty of opportunity. I'm going to count the longest carbon chain, and I can go up or down here, doesn't matter, and that contains the double bond. All right. At carbon 3, we have an ethyl. At carbon 4, we have a methyl, and I know I need to alphabetize those branches. So far, I would have a 3-ethyl, 4-methyl, and at carbon 2, there's a double bond in a 5-carbon chain. Now let's consider the stereochemistry and decide if we have an E or a Z configuration. So find the 2 carbons that are in the double bond, and that's what we have to investigate. So here are the 2 carbons in the double bond. Notice that each will have 2 bonds, right? So even though it's not drawn, we do know that a hydrogen is present. Between carbon and hydrogen, of course, the carbon is of higher priority. And in the next case, here's a carbon attached to 2 more carbon. Here's a carbon attached to 2 H's and a carbon. So of higher priority is this direction, the carbon attached to more carbon. Now just consider, here's the plane where the pi bond is. The isopropyl group over here, the carbon chain there, is above that or to the right of it, and this is to the left of it, so that's the opposite sides. So this is also the E configuration. So that's our practice, and boy, we did a good job reviewing E versus Z and how to go through naming properly the alkenes. And since the elimination reactions form alkenes, we provided a review for the nomenclature. And sometimes you're asked to just draw bond line structure, so I wanted to do some examples there as well. I go to the root word pentene, and I can see the location of the double bond. All right, so 1, 2, 3, 4, 5 carbons in the longest carbon chain, and between carbon 2 and 3 is a double bond. All right, so that's the 2-pentene part. Then I can see at carbon 3 is an isopropyl group. So a carbon leading to an isopropyl. Well, that didn't come out very clean. I'll make this green so you can see that's the isopropyl group at carbon number 3. And then at carbon 2 and carbon 4 are methyl groups. Now, why don't we see the letter E or the letter Z in this particular name? Ask yourself, is it needed? Because look at the carbon that's in the double bond. It actually has 2 like attachments. So if I switched the 2 like attachments, switching their places would not produce a different compound. So no E or Z needed. We had 2 like groups on one of the carbons in the double bond. There we go. Let's try another. So I go to the root word, 2-hexene. 1, 2, 3, 4, 5, 6. Between carbon 2 and 3 is a double bond. At carbon 2, there's a methyl group. And at carbon 4, an ethyl. 1, 2, 3, 4. There's an ethyl group. 4 ethyl, 2 methyl, 2-hexene. Why no E or Z in this name? Again, find the carbons that are in the double bond. I should have made that one too. And do you notice that 2 of the same methyl groups are on one of those carbons? So again, since that's the same group, no E or Z is needed. You know, you're not going to create a different stereoisomer by switching 2 methyl groups. You would end with the same thing. All right, great work. Another consideration is in terms of stability, really, how many carbon groups, how many alkyl groups are attached to the carbons in the double bond. So if I see a double bond and a carbon is at the terminal end, and so the terminal end would have attachments to CH2, and I see that on the other side I have just attached to one R group and another hydrogen. This is known as mono-substituted. I could have a di-substituted where I have only 2 carbons attached to the double bond. I could see that I have 3 carbon branches attached to the carbons in the double bond. Or I can see that I have 4 carbons attached to the carbons in the double bond. That would be called tetra-substituted. There's another configuration for di-substituted, and that would be to have 2 R groups on 1 carbon. And I would place that here in terms of stability, that the greater the number of substitutions on the carbon bond, the greater the stability. So just kind of thinking about this arrow that would lead this way, this would represent increased stability of that particular alkene. But if the di substitutions are on 1 carbon instead of 1 on each of the 2 carbons, it's a little less stable than a di substituted in which you see carbons on either of those carbons in the double bond. So just as kind of a practice, if you hear these vocabulary words, mono-substituted, di-substituted, tri, or tetra, find the 2 carbons that are in the double bond and count how many carbons they're attached to. So here I can see the 2 carbons in the double bond lead out to 3 carbons. This is tri-substituted. Find the 2 carbons that are in the double bond. Oops, I'll make those yellow so we color code the same. Here's the 2 carbons that are in the double bond. How many carbons are they attached to? And here I can see, as I mentioned up above, that's still di-substituted because the carbons that it leads to are off the same carbon. It's not quite as stable as if we had one on each side. Di-substituted. Ready? And I bring that up to just remind us about stability. Another consideration about stability of our alkenes is the cis conformation versus trans conformation. And you can see that there would be definite steric hindrance in the cis conformation when these methyl groups have gauche interactions. They're too near each other. And if I could spread them out on opposite sides of the pi bond, you would see that steric hindrance alleviated. So a trans conformation is much more stable in terms of energy content than a cis conformation. And you can see that on a graph that is a combustion analysis. And we looked at these in chapter 4 when we were looking at ethane, propane, butane, cyclohexane to understand the conformations and kind of twisting and Newman projections. We underwent combustion analysis. When the cis conformation combusts, it releases negative 2686 kJs of energy per mole. But when the trans conformation combusts, it releases 2682 kJs per mole. The difference there is 4 kilojoules per mole. So you can see it's costing the molecule energy to have this steric hindrance between the cis conformation. Of lower energy, more stability in the trans conformation. And you'll see that when we have options in our elimination reactions to produce a cis and trans isomer, you'll consider this trans a major product, and the cis we'll learn is a minor product. It does still form, but certainly not in the same quantity as the less, the less energy of a trans conformation. So just in mind about the pi bond is stabilized through this hyperconjugation of nearby alkyl groups. So the monosubstituted versus di, tri, then tetra shows that increasing stability. The more branching, the more stable. And I mentioned these words. Zaitsev product is more branched because it is more stable. And we'll hear this word again. The Hoffman product is the least branched and therefore it would be less stable. So associating Zaitsev and Hoffman to the major and minor products. Least substituted Hoffman, Zaitsev is the most substituted. So it's common for a substrate to have more than one beta carbon, and that can be deprotonated by the strong base. And so when this happens, we form more than one alkene product. When, let's say, for example, we have 1, 2, 3, 4. This is 2 bromo, 2 methyl, butane. I have a beta carbon next to the alpha carbon here, here, and again here. Now I color-coded those so you could see these two are actually equivalent carbons. So you really only have 2 unique beta carbons. And so when the OET, now remember what that means. Here's an oxygen on an ethyl group, right? Ethoxide. Make sure you're saying those names in your head so you can, OET, what is that? Well, it's a 2-carbon chain with an oxygen. The oxygen is electron rich. There's the negative charge on the oxygen. There are 2 beta hydrogens on carbon 3, and there's 3 beta hydrogens on each of these equivalent carbons. So if this base reaches out for a beta proton on carbon number 3, the bond collapses, the leaving group leaves, you will form, in this particular case, 1, 2, 3, 4, your Zaitsev product, the most substituted alkene, becomes 2-methyl-2-butene. There are 1, 2, 3 substitutions. Tri-substituted is the Zaitsev product, more substitutions. But also, had we abstracted a beta proton from carbon number 2, from carbon number 1 right here, or this would be carbon number 1. If we take it off the very beginning carbon, you would form what's called a di-substituted alkene. And that would be of less substitution, less stable. That's known as the Hofmann product, least substituted. So in this particular example, the minor product is Hofmann and the major product is Zaitsev. And you can start to figure out, what if I wanted the Hofmann product to be the major? How could I design a synthesis to make sure I get the least substituted? And that's a very good question. Selecting the appropriate base can lead you there. So an elimination E2 is very regioselective. When constitutional isomers are forming, more than one possible product is a result. It's called regioselective. And that's saying that I have an opportunity to take a proton from this beta carbon, or I have an opportunity to take a beta proton from this beta carbon. Which one is going to win? Well, the answer is both occur, but the regioselectivity of an E2 can be controlled by selecting a base. If I select a small, strong base, it has no problem abstracting the beta proton from the carbon at position 3. And this would be the major product, the most branched, Zaitsev. The least branched, Hofmann, would be the minor product. Because I used a small base, small meaning that it's not bulky. The strong, small base favors the Zaitsev. No problem getting in there to abstract the beta hydrogen. But what if I selected a base that I wanted to use to favor the Hofmann product? I start using what are called big, bulky bases, such as tert butoxide. Now look at what that is. There's a carbon attached to 3 other carbons, and there's your oxide, a big, bulky base. Or instead of this, what if you had ethyl groups? That's even larger, isn't it? So this carbon is attached to 2 carbons, attached to 2 more carbons, attached to 2 more carbons, and there's your oxide. Those are big, bulky bases. So if this is your target, there's steric hindrance preventing it from reaching that secondary carbon, a carbon that's attached to 2 other carbons. Call it a di-substituted carbon. But over here, this out in the open, this hydrogen really is not associated very close to anything at all. This hydrogen is very easily plucked off, even by a big bulky base. So you make the least substituted the major product when you use big bulky bases. You make the Zaitsev favored when you use small, strong bases. So you can control, based on the selection of your base, which side of, which stereochemistry do you want to produce more of? The least substituted can be favored, the Hofmann is the least substituted, by using big bulky bases. If you want the most substituted, which is the Zaitsev problem, select a small, powerful base, and you'll make the most substituted alkene. So why does this sterically hindered base favor the Hofmann product? And it just really is considering steric hindrance. Tert butoxide, you'll see that is T-B-U-O-K on the arrow. I need you to envision what this is. This is the spectator ion, just like a sodium could be used. It's only there to keep charges electrically neutral. But here, this is a big, bulky base, all of these carbons with their 3 hydrogens coming off. So tert butoxide, 1, 2, 3, 4 carbons is the but, and this carbon has 3 carbons coming off. That's the tertiary part, tertiary butoxide. Diisopropyl amine. So this is the amine functional group. And if 2 of those substitutions are isopropyls, that's that 3 carbon unit here, diisopropylamine, that's big bulky base, isn't it? Here's the nitrogen electrons that are going to act as the base. And you could even have triethylamine around the nitrogen's 3 bonds or ethyl groups. That would qualify also as a big bulky base. When you're using these big bulky bases, they favor the Hofmann product. And the Hofmann product is the least substituted. A small, when I mean small, say sterically small, sterically unhindered, you're going to favor the Zaitsev product, which is the most substituted product. So what might that look like in terms of a practice problem? Here's a homework question. It says, predict the major and minor products for the following E2 reactions. So sodium ethoxide, sitting on the arrow. Here's what I want you to envision. Sodium ethoxide. Sodium is the spectator. It's not part of the chemistry at all. But I do have an ethoxide, which is 2 carbons connected to the oxide anion. So this is not sterically large. It's a small base. Now, I'm going to locate the beta carbons. Those 2 are beta carbons, and this is a beta carbon. The alpha is the carbon that's attached to the halogen, right? The alpha carbon is attached to the halogen or the leaving group. And the beta positions are 1 position away. So what do we have available for elimination? Well, there's 3 hydrogens on this particular terminal branch. There's 3 hydrogens there in a beta position. There's 2 hydrogens here in a beta position. And this is also beta, but there's no hydrogens there. So that's not a possibility. So now we're down to just 2 beta positions. Alrighty, with a small base, the most substituted alkene will be favored. Remember the pattern here, the OET, it's going to abstract a proton. That bond collapses and the leaving group leaves, all in one concerted step. We would form the conjugate acid of our base, which you'd see then as HOET. You would see the leaving group, that's your conjugate acid, that's your leaving group with its extra electrons. And in terms of the third product, the most substituted alkene would be the Zaitsev product, where you'd have 1-methylcyclohexene as your most substituted, which would be Zaitsev. I meant to say this is your major product, Zaitsev, most substituted, but you can have a competing product where you had the least substituted alkene form, and that would give you a double bond leading to the carbon that was this original methyl group over here. And so this would be the minor product, which would be the Hofmann product. So we can form a double bond within the cyclic structure or out to the original methyl group attached to the alpha carbon. Here's a next example. We have 1, 2, 3, 4, 5 carbons in that chain. Locating what we call the alpha carbon. The alpha carbon is the carbon attached to the leaving group. From there, find all the beta positions, which is 1 position away. So I've highlighted the beta position. Do you see that these two are equivalent? They're just both methyl groups. So I really have 2 competing positions between carbon 2 and 3 and between carbon 1 and 2. Sodium is a spectator. Your base is hydroxide. When the base abstracts a proton from carbon 3, the bond collapses and the leaving group leaves. We'd have 1, 2, 3, 4, 5 carbons in the chain leading out to that 2-methyl, and the double bond would be between carbon 2 and 3. 2-methyl, 2-pentene. And this is the Zaitsev, the most substituted, and it would be the major product. But we could have also formed 1, 2, 3, 4, 5. We could have formed the double bond between carbon 1 and 2, and that would have been the Hoffman product, the least substituted, and that would have been the minor. And that would have a name of 2-methyl, 1-pentene. And notice I do not need an E or a Z in this configuration because I have like attachments. And here, even though they're not shown, those are 2 hydrogens, so they're alike on one of the carbons in the double bond. If it's attached to 2 like groups, it's impossible to have an E or a Z or cis-trans configuration. So our name is perfect without that stereochemistry. All right, so now what happens in the next example? Here we have an idea where we have 1, 2, 3, 4, 5, but we're using a big bulky base. The big bulky base is tert butoxide. Potassium is your spectator. K plus is your spectator, so just ignore that. But a big bulky base is going to favor the Hoffman product. So when we end up showing this guy, the double bond between carbon 1 and 2 will be the major product, and in minor product will be the Zaitsev. Big bulky bases do not favor the most substituted. So here we've just selected a big bulky base to favor the least substituted Hoffman product. I've been talking about an hour. I wanted to just check that time. The next lesson also deals with E2, but I'm going to pause for a moment, give yourself a break, and come back for a next lesson on E2. Very, very critically important in predicting the correct stereochemistry for E2 reactions. Take a break and come back for the next part of elimination reactions.